Hello APC Mechanics students, today we'll solve the past paper FRQ 2022 Set 1 exercise number 3. Then as usual we expect that the figure should be above the text. Then let's start reading. A solid uniform disk, uniform means the mass distribution is the same and the center of mass is located geometrically at the center. Is supported by a vertical stand. The disk is able to rotate with negligible friction. Then we can use conservation of energy, if any. About an axle that passes through the center of the disk, the mass and the radius of the disk are given by md and r respectively. The inertia of the disk is half mdr square. A string of negligible mass is wrapped over the disk and attached to the top of the disk at point P. One end of the string is connected to an unstretched ideal spring. Ideal, it means we can apply Hooke's law of spring constant K, which is fixed to the ground as shown in figure 1. Okay. Now a block of mass mb is then attached to the string on the right side of the disk. The block is slowly lowered down until the spring disk block system reaches equilibrium as shown in figure 2. In this equilibrium position, the disk has rotated clockwise through a small angle theta, and theta is the angle with the vertical. Give all algebraic answers in terms of mdr, k, theta, and physical constants as appropriate. So now whenever we determine an expression, we need to make sure that it's being expressed in terms of these. Then going on to the next page. Now we need to derive an expression for the mass mb of the block. And notice that the system is at equilibrium. Then we can directly say then torque net is equal to 0. All of the torques are balanced. Now what are the forces acting on our disk? We have the pull of gravity of the disk. So this is, let me say, Fg. We have the force at the axle. We have the force provided by the spring, and we have the force provided by the tension, which is equal to the pull of gravity of the block. So here let me say the torque G, which is due to the gravity of the disk, plus torque at the axle, plus the torque provided by the spring or the tension, plus the torque provided by the spring, that would be equal to 0. Now we can ignore these because the forces passes through the axis of rotation. Now here in both cases, you know that the definition of the torque is force times distance times cosine of the angle between the force and the tangential, but notice that these two forces, they are applied tangentially, so no need for a projection. Now I will suppose, so the tension here, the force of the tension is equal to mbg, and it provides a torque in the negative direction, and the force of the spring provides torque in the positive direction. Therefore I'm gonna say that minus mbgr plus the force of the spring multiplied by r is equal to 0. And here we can directly say that Fs is equal to K multiplied by the elongation of the spring. The elongation of the spring is not given, so I will name it to be X. But here we suppose that there is no slipping between the string and the disk. Therefore, if this has been elongated by delta X, then the disk will rotate by r theta, because we know that linear displacement is related to r via s is equal to r theta. So that would be equal to r theta, sorry, k multiplied by r theta, because we need to express our answers in terms of these and we don't have the elongation of the spring. Now therefore, so which means that mbg r is equal to k r theta multiplied by r. Now r with r would cancel, and we're interested in determining mb. Then mb in this case, the mass of the block would be given by the expression which is k r theta divided by g. Now this is it for part A. Now in part B, they're telling us at time t is equal to 0, the string on the right side of the disk is cut and the block falls to the ground. On the circle below, which represents the disk, draw and label the forces, not components, that act on the disk immediately after the string is cut. So Again, the angle is given by theta and the block is falling to the ground. Each force should be represented by an arrow that starts on and it's directed away from the point of application. So basically we have, since we need to draw the rigid body diagram at the exact time t is equal to 0, then we have the same forces given by the 4 forces, but we can eliminate this one because now the string is cut. Therefore, we have the pull of gravity on the center of the disk. So remember here in this case, we need to represent the forces properly from their point of application. So that would be the pull of gravity. And we have the force at the axle, which balances the pull of gravity upward like that. And we have the force which is applied tangentially to the rim of the disk, which is the force of the spring. Now, derive an expression for the angular acceleration alpha of the disk immediately after the string is cut. We know that alpha in such type of exercises always and forever is determined by Newton's second law. Then let me write apply Newton's second law, because this is a big law. We need to mention the law that we're using. It's not important whether we write down for rotation or for translation. And this is given by tau naught is equal to I multiplied by alpha, and here notice carefully I would represent the rotational inertia of all the system that includes the mass. Now, what are the different forces from the previous part, or torques, forces that provide torques? We have the torque due to the gravity plus the torque due to the axle plus the torque due to the spring is equal to I alpha. Now we can directly eliminate these. Now, considering the positive direction to be counterclockwise, the force provided by the string, as we have determined here, is given by kr theta, because we're still determining the angular acceleration alpha for which instant immediately after the string is cut. So as if we have stop time, and the angle is again given by theta. So that would be the force of the spring multiplied by r. The force of the spring is given by kx, and x is given by r theta. So that would be given by k r theta multiplied by r, which is equal to the rotational inertia of the system. Now here, after the block has been removed, the only only body that has rotational inertia is that of the disk, and the rotational inertia of the disk around the center is given by half mdr square. Then we can safely here say that this is given by half mdr square multiplied by alpha. Notice that this cancels with these. Then we have k theta is equal to half md multiplied by alpha, and we're isolating for alpha. Then alpha in this case is given by 2k theta divided by md. Notice here carefully that alpha is proportional to the displacement, which means that we're talking about specific type of motion due to a restoring force, and we know that this type of motion would be oscillatory motion. And whenever we need to plot the variations of omega or alpha for such type of systems, we know that they will be related to a cosine or a sine function, because simply the acceleration is related to the position, or alpha is related to theta, or proportional. Now we know that the sine function would be something like this, and the cosine function would be something like that. Now if we're interested in plotting the magnitude, so we can ignore these two parts, then we're limited to two types of curves, either 1 or 2, and similarly here, either 1 or 2 or 1. And this depends on the problem. If omega is increasing, then omega would be represented by 1. If omega is decreasing, it would be represented by 2. Then let's check. At t is equal to t1, the disk has rotated, and point P is again directly above the axle. So what's happening here, that at t is equal to t1, the disk has rotated, and the point P is again directly above the axle. Now initially we have started from the point P at equilibrium at t is equal to 0, P is here. Then from t is equal to 0 to t is equal to t1, P will move from this point to this point, and as you can notice that P is moving from, you can think about it from the amplitude of oscillation to the equilibrium position, and we know that whenever we're going from the amplitude to the equilibrium, we expect that the angular speed would increase, and indeed we're interested in determining or plotting the magnitude of the angular velocity. For this reason, as we've stated here, that it should be part of a trigonometric function, sine or cosine, but it's concave downward, so it's like that. Okay, moving on to the next page, and that would be the final part of this exercise. They're telling us, okay, in part E, the disk is adjusted on the support so that the axle doesn't pass through the center of mass of the disk. Previously, the axle was being located at the center of mass, but now the axle is being shifted to the left, such that now the center of mass is located to the right. The block is again hung on the right side of the disk, and the spring disk block system comes to equilibrium as shown in figure 3. The axle does not exert a torque on the disk. So in the previous configuration, there is no force due to the axle, neither here, so it doesn't change. For each force on the disk, we're talking about which forces. We're talking about the force of gravity, we're talking about the force provided by the tension, and we're talking about the force provided by the spring. Indicate whether the magnitude of the torque about the axle caused by that forces increases, decreases, or stay the same relative to part B. Alright, now since we're interested in talking about the magnitude of the torque, remember that the torque is basically force times distance times cosine of the angle. And here we're assuming that all forces are being applied tangentially, including the gravity, so we can ignore this one. So now the torque is being affected by two things, by the magnitude of the force itself and by the lever arm or the distance from the axis of rotation. Now let me start by the torque exerted by the gravity on the disk. So the torque exerted by the gravity on the disk, which is basically the pull of gravity of the disk itself. In the previous part, this force didn't provide any torque because simply it was passing through the axis of rotation, but now this force is being acted on the center of mass, and now you have it's been shifted from the axis of rotation and we have some distance. So initially the torque provided by gravity is 0. Now it changes to a value which is non-zero, so the torque increases. Then let me say it increases from 0 to a non-zero value because now it has a non-zero lever arm. And now let's continue with the torque exerted by the tension. And here we're talking about the tension provided by the string and not the spring, by the tension in the string. And remember, the torque, it's about force and distance. Now here, the force didn't change in magnitude because it's also again equal to mb multiplied by g. But notice that the distance increased from this part to this part because the axis of rotation has been shifted to the left, so which means the level arm has increased. So it increases because the level arm is now longer. And now finally we need to discuss the torque exerted by the tension on the spring. And that would be the tricky part. I will explain why. At the first glance, in comparison and what we have discussed in the first two torques, you would directly say that the torque exerted by the spring is Fs multiplied by the lever arm. So this is Fs and this is the level arm. Compared to the previous discussion, this have decreased, and you will directly think that so the torque provided by the spring decreases, and that's completely wrong, because we don't know explicitly what's happening to the force of the spring, because this depends on Hooke's law, which is given by Kx. However, because it is at equilibrium, and in order for this to be in equilibrium, the torques provided by the block and the pull of gravity of the disk should balance the torque provided by the spring. So the torque of the spring should be equal to the torque provided by gravity plus the torque provided by the tension. Because each of these separately increases, then we expect that the torque provided by the spring increases. Therefore, this is a bit tricky. So let me say here it increases. To balance the torques provided by the other two forces since their torques increased as well. And that's it for me in this video, guys. See you soon in a new one.